Let's get started. Again, ma, and the lighter. Okay, shall we get started? How was the test? Okay, easier, tougher, medium, but questions at least புரிஞ்சுதா? எனக்கு ஞாபகம் இல்லை கொஸ்டின் தான் சார். What was the question? Square of a அது வந்து you have to apply that formula mu naught I by 4 pi into sin alpha sin pi 1 plus sin pi 2. அந்த ஃபார்முலா அப்ளை அந்த ஃபார்முலா அப்ளை பண்ணும்போது sin pi 1 and sin pi 2 ஸ்கொயரா இருந்தா it will be 45 degrees 45 degrees. அதுவே ரெக்டாங்கிள்னால you have to apply the trigonometric ratio and then take it. b by 2 l by 2 ன்னு போட்டு பைத்தகோரஸ் தியரம் அப்ளை பண்ணுங்க. The same thing you will get that by doing this only. Okay. But I don't think did I tell that for did I teach that for you somewhere else? I gave that as a special case, no? So I gave four cases then. First is at the infinite length at the center, then infinite length at one of the points. Correct. I remember. Yeah, third point. Yeah, use it. It's the same concept that you need to use. Notes la bar irukana. Idhula irukku nadi oru. So idhar irukla. Shall we start? Play. Start பண்ணலாமா? உன் பர்மிஷனோட. நை பேசிட்டு இருக்கேன் மூணு பேர். அப்படி என்னதான் பேசுறீங்க? நாளைக்கு இருக்கா ஸ்கூல்ல? டான்ஸா? பண்றா சும்மா ஒரு நாள் தானே. One day only, no go. Till what time is the school? அதுக்கப்புறம் போய் தூங்கிடு. அதுக்கு என்கிட்ட ஆன்சர் இருக்கு. உனக்குலாம் காலங்கத்துல கிளாஸ் வச்சு செத்துருவ போல இருக்கேன். அதுக்கு என்ன பண்ண முடியும்? நீங்க போயிட்டு வாங்கம்மா. எல்லாம் இதே மாதிரி நினைச்சு பங்க் அடிச்சா அப்ப யாருமே இருக்க மாட்டான். கரெக்டா? டைம்ல தூங்க. நான் கிளாஸ் எடுக்கிறப்ப ஸ்கூல்ல நல்லா என்ஜாய் பண்ண. நான் கிளாஸ் எடுக்கிற மட்டும் வாயை பெருசா தொடங்கி இப்போ போட்ட மிஸ் மாதிரி. என்ன வேணும்? ஒண்ணும் இல்லைல்ல. எதை பண்ணலாமா? நைஸ் வெதரா? என்ன வேணும்? ஆ? என்ன வேணும்? சமோசாவா? ஆப்ஷன். So he will talk for you, you will talk for him. He will talk on behalf of everyone. Huh? What do you want? Samosava. Solra? Sure. Anybody wants samosa? He's saying weather is nice. He wants to enjoy. He wants a samosa. Tea, coffee, Bonvita, boost, etc. Horlicks. இங்க கிளாஸ்ல வாயை தொடர்ந்து முடிஞ்சதுக்கு அப்புறம் சரியா? ஆனா வாயை திறந்தா கூட பக்கத்துல இருக்குன்னு அப்படி சாப்பிடணும். இட்ஸ் யோர் ரெஸ்பான்சிபிலிட்டி. சரியா? வாயை திறக்க கூடாது. அப்படி அப்படி போட்டு this standing valid. அப்ப நான் வந்து I'll get you. மேக்ஸ் கிளாஸ் முன்னாடியா? சரி. பட் எங்கேருந்து வர வைக்கிறதுன்னு யோசிக்கும். பாக்குறேன். சரி, we'll get started. Listen. Cursor is there? Okay. So the fifth chapter is magnetism and matter, right? So if you look at the fourth chapter, what is the name of it? So moving charges and magnetism, right? So if you observe, I'm able to see the word magnetism here. I'm able to see the word magnetism here, right? So fourth chapter also dealt with magnetism. Fifth also we are speaking about magnetism. Then why do we need two separate chapters for the same concept? See, logic is very simple. If you look at the prefix right here, we are saying that you have magnetism generated as long as the charges are in motion, right? So once the charges are going to stop, magnetism is lost. Whereas when you talk about this one, it is magnetism and matter in the sense we are going to discuss about the magnets which have magnetism within them, irrespective of whether you pass current or not. So to put it very simple, here the kind of magnets we did temporary magnet. So what are the temporary magnets? Basically electromagnets in the sense, as long as electricity is passed, magnetism is exhibited, right? Whereas here, what are you going to deal with? You're going to deal with permanent magnets, right? So we need to understand one thing clearly, that the fourth chapter clearly tells us one thing, that magnetism can get generated in a material only when there is a charge in motion, only when there is electric current, right? So to put it simple, whenever you want the concept of electric field to exist, you can think of charges at rest, right? So you put the charges in motion, it becomes current electricity. And if there are charges in motion, there is going to be a field around it, which we call it as magnetic field, which is going to be in addition to the existing electric field, right? But see, this one, since you're talking about it is current to generate magnetism, but talking about permanent magnets, how does that material have magnetism acquired? Are you able to understand? So that is the first question we need to answer. So when you say moving charges are important for you to generate magnetism, in this chapter, what are we doing? You take a wire and you connect that wire across a battery source or a potential difference source. Then what will happen? As soon as the charges start flowing within them, you can see that magnetism is exhibited. Means if you take a thin wire like this, okay, you take a wire, you connect it across a battery. Let's say you connect it across a 9-volt battery. You take that wire and place it close to iron filings, you can see that the iron filings will start getting attracted. Maybe it will not be that strong, but they will start getting attracted. Means that shows that magnetism is existing. But here, when I talk about a permanent magnet, where does this acquire magnetism from? Because we are not connecting this across any potential source. Then who is that moving charge which is having or which is giving the property of magnetism to this material? If I take another magnet, you know what this is? It's a bar magnet and the horseshoe magnet. So if I take them close to each other, see, you're able to see I'm not doing anything. It is turning on because the like poles. Here it is getting attracted. So here it should, this is happening. I'm able to sense some force. See, right? Question is, where does this get from? Where does this get the magnetism from? Answer. And the answer to that is, we know that every material in this world is made up of atoms, right? So when everything is made up of atoms, the first thing that we need to understand is what is the magnetic dipole moment of a revolving electron? In the sense, what does an atom have? Atom has electrons in the orbits, and you have the protons and the neutrons inside the central core called as the nucleus, right? Now, what is going to happen to it? When I think of an electron that is revolving in an orbit, right? When I think of an electron revolving in an orbit, let's say the orbit's radius is r, okay? Now, let's say its speed is v. So, speed is always taken tangential to the surface, right? Now, what I'm trying to say is, when this is in motion, then the particle acquires magnetism. In the sense, we know that every material in this world is made up of atoms, including you and me, everyone. So, wherever the atoms are going to be in motion, you're going to have magnetism generated by that particle. But the question is the extent of strength that is possible. So, that depends on the type of the material it is going to get divided into. So what we are going to learn in this chapter is, first we will understand where the magnetism is acquired from. That is clear that it comes from the revolving electron. So based on the way those magnets behave, they are basically classified into three main categories, namely paramagnetic, diamagnetic, and ferromagnetic. So to understand that concept, we first need to understand this. So am I clear with this point? So what is it? For this permanent magnet to acquire magnetism, what should be there? There should be an electron that is revolving in an orbit around the nucleus. Is the point clear? So we are going to find out what is the mathematical value of the magnetic dipole moment that is getting generated due to this revolving electron. So having said that, shall we get started? All right. First, the radius and velocity are going to be perpendicular to each other. You know that. They're going to be perpendicular to each other. So when the electron is revolving in the anti-clockwise direction, what is going to be the direction of current? Current will be in the clockwise direction. So first thing is, since I need to calculate the magnetic dipole moment, I know the basic formula of magnetic dipole moment as I into A. It is I into A. So here, what is the value of I? I is equal to Q by T. So Q is going to be the electron, the charge of the electron that is revolving, and the time is going to be the time period it takes to complete one revolution. Right? So it is going to be E divided by, what is the time period? Formula, distance by speed. So what is the distance? 2 pi r divided by the speed with which it is moving is v. So it is E into v divided by 2 pi r. Am I clear? So I is equal to E into V divided by 2 pi r. Let this be equation number 1. But what is our interest of study? It is a magnetic dipole moment. I should not stop it with current. I should multiply the current with area to get a value. So when I do that, I get M is equal to I into A. No, it is not cross. It is I into A. Okay. So what is I here? It is EV divided by 2 pi r into what is going to be the area? Area is going to be pi r square. So r and r will get cancelled. Pi and pi are gone. It is going to be E into V into R, the whole divided by 2. Right? Which is going to be the magnetic dipole moment. But remember, this is not the final expression we are going to write. Because whenever you derive any equation in physics, right, or for that matter, any subject, whenever you derive an equation, that equation should be in such a way that it should support you in the lab. In the sense, you should have only those parameters in the equation which you can actually find out from the lab. So here, if you observe, magnetic dipole moment is charge multiplied with V multiplied with R. So it is not possible for us to calculate the value of V and R. So what we'll do is, I'm going to do some manipulation to it. Observe. Okay. So magnetic dipole moment is equal to, small m is for magnetic dipole moment. Now what I'll do is, I'll multiply it with the mass of electron and divide it with the mass of electron. Observe. So m with a subscript E into EV R, the whole divided by 2 times mass of the electron. Am I clear with this? So mass of the electron into speed into R is going to give you what? So there is a physical quantity called as angular momentum, which is given by the formula R vector cross P vector in terms of vector parameter, or you write it as RP sin theta in terms of scalar, right? So this can also be written as MVR sin theta, because linear momentum is mass into velocity. So MVR sin theta, when you put theta is equal to 90 degrees, right? So theta is the angle between the velocity vector and the R vector. So when theta is equal to 90 degrees, sin 90 is going to give you 1. So it will be MVR. So what happens here is ME into V into R is going to be the angular momentum. So this will become E divided by 2 times mass of electron into the angular momentum. Angular momentum is represented with the symbol capital L. Is the point clear? Okay. Now we need to understand one point, that magnetic dipole moment is also a vector quantity. Angular momentum is also a vector quantity. Now, how are they both related? So this is the expression m is equal to E divided by 2 me into L, right? So when I write this expression, I need to find the direction of each. If I look at the direction of angular momentum says R vector cross P vector. So take your right hand. When you're doing cross product from the first vector, curl your fingers towards the second vector. R vector cross P vector. P is the direction of the velocity itself. R vector cross P vector is going to be in this direction. So angular momentum in this case is out of the plane. Whereas when you talk about the dipole moment, for dipole moment, since this is the direction of electrons revolution, the direction of current will be in this way. So direction of current is clockwise. So what you're supposed to do is take your right hand, curl the fingers of your right hand in clockwise direction, and point your thumb. That will be the direction of magnetic dipole moment. So what is happening here? Magnetic dipole moment is into the plane. Angular momentum is out of the plane. So they both are in opposite direction. So when you write it in the vector form, when you write it as m vector, so m vector is going to be equal to E divided by 2 times me into minus L vector. So this is the scalar value, this is the vector value. Am I clear with this? Yes, right? Okay. Now what I'm going to do is, I'm going to write L also in terms of few known parameters, right? So for that, what I'm going to use is, I'll use the condition of Bohr's quantization. So I'll use the Bohr's quantization condition. So what does Bohr's quantization condition state? The angular momentum of an electron is an integral multiple of h by 2 pi. So L is equal to NH divided by 2 pi. You remember this? This you would have learned in your chemistry in atomic structure. So angular momentum is equal to NH divided by 2 pi. So let me call this as 2 and let me call this as 3. If I use the third in second, what will I get? M will be equal to E divided by 2 times ME into NH divided by 2 pi. Am I clear with this? So it is going to be N into EH divided by 4 pi times ME. So this is going to be the magnetic dipole moment of the electron, which is revolving in a orbit. Okay. Now the question is, if you observe, all these parameters are known to us. You know the charge of the electron. H stands for Planck's constant. You know the value of it. 4 pi is constant. Similarly, you know the mass of the electron also. Only thing that changes is n. Okay. So, in this expression, so in this n into EH divided by 4 pi times ME, if I put n is equal to 1 and substitute all other values, E is equal to 1.6 into 10 power minus 19. H is how much? 6.626 into 10 power minus 34 joule second. 4 pi is 4 into 3.14. And the mass of the electron is going to be 9.1 into 10 power minus 31 kilogram. If you take all these values and substitute it here, then M will come out to be 9.27 will be 9.27 into 10 power minus 24 ampere meter square, right? And this value of 9.27 into 10 power minus 24 is what is called as Bohr's magneton. Is the point clear? So it's called as Bohr's magneton, right? So is the point clear? So just to summarize, if you come from the beginning, what is that we understood? That every particle in this world is made up of atoms, and atoms have electrons which are revolving in the orbit. And due to those electrons, what will happen? There will be a magnetic dipole moment that will get generated. And due to that magnetic dipole moment only, every material is going to exhibit magnetism. So for that, the mathematical derivation is this, right? So just make a note of it. L is outside. R vector cross V vector outside. For magnetic dipole moment, current is in the clockwise direction. So curl your fingers, it is in. Done? Copy this. Done now? Listen. So the next topic that we'll discuss is about artificial magnets. So if you look at it, when you talk about a natural magnet, so the natural magnet is you take this magnetite. So what will happen to this is this will exhibit magnetism, but it will not be strong enough that you can use it for commercial or industrial purposes. So what do we need to do is we need to make sure that this naturally occurring magnet is converted into an artificial magnet, right? So when you talk about the different kinds of artificial magnet, the first one which is commonly used is a bar magnet. So generally what happens is whenever you design a magnet, no, it is always important that you give color. See, for example, there is something written over here, north and south. But suppose I show you like this, and I ask you which is North Pole and which is South Pole. First thing, you'll not be able to see anything. If at all you are able to see also, you'll not be able to figure out. So instead, what we can do is, if I give you color just as a code, it will be easy for you to identify even at a longer distance. That is the reason why this code is given, color code. So red is given for north and blue is given for south. Second, you can think of a magnetic needle. So where do we have this magnetic needle? Mostly it is used in the compass. So what does this magnetic needle do? So when you say it's a magnetic needle, magnet placed in the presence of external magnetic field will experience torque. So magnet placed in the presence of external magnetic field will experience torque. In the sense, this is there, no. So it is a thin magnetized steel needle having pointed ends and it is pivoted at its center so that it is free to rotate in a horizontal plane. So when it is rotating, no, it will rotate in the horizontal plane. At the same time, it will vibrate also like this. This is something called as dip. The question is, When you look at this magnet, why do we use a compass in the first place? For navigation, right? Yeah, for knowing the directions. So when I say navigation, the point is how is the pointer able to rotate? Where does it get the magnetic field from? You're not taking another magnet and keeping it closer, no? So how does that happen? It is because of the Earth's magnetism, right? Because of the Earth's magnetism, you can see that it is rotating. But as I told you, no, while it is rotating, it will also move like this, which is called as dip. Okay. So this is also a magnet, but not a very strong magnet, right? Third, you can think of it. So this is a horseshoe magnet because it looks in the shape of a horseshoe, right? So it has the shape of a horseshoe and thus named like that. So there is something else called as a ball-ended magnet. Again, if you see, this also has a color code. What is it? Red is used for north and the blue is used for south. The same logic. If you see all the four, there is a color code that is used. So wherever red comes, it is north. It is understood. Am I clear with this? So this is all about artificial magnets, right? Point is, these magnets exhibit certain basic properties, right? That's what we call it as the basic properties of magnets. If you look at it, we look at them one by one, okay? So when you talk about the magnets, the first thing is, see, here I am taking it close. It is getting attracted, right? So here we are talking about attractive property. So when you talk about the basic property of a magnet, it can get attracted at the same time repelled also. But the main property we are going to talk about is going to be the attractive property. See what attractive property we are talking about. Thing is, when you have a magnet, what kind of a particles can it attract? It can attract the iron or the steel particles. So that's how we generally test something, right? When you take closer to an iron particle or a steel particle, it is going to attract them, right? So when you take a small pieces of iron, cobalt, nickel, etc., when you bring this magnet, see, thing is, you're not going to go and touch it. Here also, if you see, I didn't go and touch it like this. I didn't go and touch it. I keep it close itself. It is automatically pulling my hand. Okay. So when you take it closer to that substance, closer to that particle, what will happen is, so what particles? You can think of heap of iron filings. Okay, iron filings in the sense, small pieces of iron that is scraped out. That you would have seen it, it will look like brown color dust, right? So when you take the iron filings close, the first thing that you can observe is the ends of the magnet show the greatest attraction. And why is it going to happen? Because the ends of the magnet is going to have the poles. It is going to have the north pole and the south pole, meaning more amount of magnetic substances. So understand two things, okay? One is a magnet and the second is a magnetic substance. So here, the one which contains the north and the south pole is going to be the magnet, whereas the one which is getting attracted is called as the magnetic substance. So here, iron filing is the magnetic substance. So you can observe that more amount of magnetic substance is present near the ends of the magnet, which is basically the poles. Why is it so? Because the strength at that point is going to be very high, right? This is what we call it as the attractive property, right? So these ends where the magnetic attraction is maximum are called as the poles of the magnet. And an important point to be noted is every magnet will always have two poles. Okay, every magnet will have two poles. Am I clear with this? Right? Yes. So just make a quick note of it. That's how magnet will happen. North and south is enough for you to, okay, because it's the axis define பண்ணும்போது ரெண்டு poles தான் பண்ண முடியும். Then you should have like this and like this. There is no material like that. தேவையில்லை. It is understood that the other directions are. If you know one of the poles, in fact, you need not know north and south. North isn't there. Can't you tell what is east, what is south? That is only a reference. But north and south are considered to be the important poles of. Clear with this? So this is the attractive property. Shall I proceed? So this is another important thing, which is called as the directive property. Okay. Who's good at recording who can handle camera better? Camera handle பண்றியா? Diva. நான் இப்போ உனக்கு காட்டுறேன் அது வீடியோ போர்ட்ரேட் அப்படியே உட்காந்துக்கோ நீயும் பாரு I'll show something so that நான் உனக்கு காட்டுறேன் அந்த டைம்ல because I want to record this. See, this is a very important property. Okay, listen to this. Start பண்ணிடு. நான் தெரியறேன்ல. Okay. So the next property that we'll discuss is the directive property. Right? What does it state? When a magnet is suspended or pivoted freely, it aligns itself in the geographical north-south direction. The pole of the magnet which points toward the geographical north is called as the north-seeking, and the other pole which points towards the geographical south is called as the south-seeking or south pole of the magnet. Now the question is, I told you that a compass has a magnetic needle, right? So how is it able to know that there is a direction? It is because of the Earth's magnetic field. Now, what I'm going to do is, let's say I'm giving you a task where you need to design your own compass. What are you going to do? You're going to design your own compass. Let's say I have this in my hand. Now you don't know what is the direction. You're navigating. You don't know what is the direction. So what are we supposed to do? There is an important basic property exhibited by magnet. What is it? Directive property. So when you take this and suspend it like this, so when you suspend it freely, you're able to see it is rotating. No, there will be on one particular point at which it is going to be stable. I didn't stop it though. See, it started rotating because of the torsion. It was wound. No, the string had some torque present in it. Due to the torque, it was rotating. Now, if I hold it like this, you're able to see. So what pole is getting directed? Can you see? What pole is getting directed? You tell. So when I hold it like this, no, so this point is actually south. It is south. So it is saying that this direction is the south. Okay. But how will I get a validation? Obviously, I can think of a compass. So generally, when you navigate, right, you're not going to hold the compass like this. How will you hold it? This way. So this is because we are going to navigate along this direction. So north, south, east, and west. When you look at this, if you observe, can you focus on this? So what direction is getting pointed here? So you're able to see south, right? So if you observe, do you have any, does anyone have a compass in your mobile? You have it? So that side, yeah, sorry, not mobile watch, yeah. Yeah, north and this side will be south. So what I'm trying to say is, when you suspend this magnet, right, south pole is facing in this direction, and that is validated with the help of this compass itself. Right? And this property is what is called as the directive property. Cut one. Okay. So did you guys understand what is the meaning of it? Oh, no problem. Okay, thank you. Are you clear with this? This is a very important thing. So why is this directive property important? It is important for the navigation, right? Because we should know which is the North Pole and which is the South Pole. That is why if you remember in the previous chapter also, when we were solving problems, we took north like this, south, we took north, south, east and west, if you remember. So most of the cases, you will take it horizontally only. And what north and south pole are you talking about? They are the geographical north and the geographical south. Is the point clear? So just make a quick note of it. Done? So the third property is going to be like poles repel and unlike poles attract. There's no, right? If you take two magnets and suspend them in such a way that if the north pole of the magnet, if the north pole of the first magnet is coming closer to the north pole of the second magnet, they are obviously going to repel, and the vice versa is going to happen for the reverse poles, right? So that's what the third property says. It says like poles repel and unlike poles are going to attract. The fourth point is, when you talk about magnetic poles will always exist in pairs. In the sense, if you take this magnet, okay, if you take this magnet and let's say tomorrow you're going to break it into two pieces, right? So this is how the magnet is going to be, north and south. If it is broken here, then this will be a small piece, this will be another small piece. Let's say you're breaking it into two equal parts. It is not like that this is going to be north pole and this is going to be south pole. Remember, unlike the electric charges, where in electric charges, monopoles will exist. That is, you can think of an isolated positive or an isolated negative. There is nothing like an isolated north pole or isolated south pole. North and south pole in the magnet will always exist in pairs. So this will have north-south, this will also have north-south, but the difference is going to be in such a way that if this has a strength of, let's say, X, right? When you break it into two equal parts, this will have a strength of X by 2 and X by 2, provided you break it into two equal parts. Suppose you're going to break this further. So the ratio according to which you're breaking it, it will change, the strength of the magnet will change in accordance. Is that point clear? Right. And the last point that we need to know is magnetic induction, right? Generally, what happens is a magnet induces, right? What happens? A magnet induces magnetism in a magnetic substance placed closer to it, right? This is a magnet. This is a magnet. Okay, just give me a minute. So you take some bell pins. Okay. We take some bell pins like this. Now, what I'll do is, I'll take this pole closer to this. Did you understand what happened? Did I touch it? I didn't know. But when I took it closer, what was actually happening? This magnet has a field around it. And that field will start inducing magnetic field in this. That is why there was no physical contact, to understand that. So without any physical contact, you can see that it will come and get attracted because it will use the air medium and start inducing magnetic field inside this. So that I took the south pole closer to this magnet. So it will start generating this end to be the north pole and it will push the south pole to the other end. So that this bell pin is also starting to act like a small magnet. You can think of this like a magnetic needle of the compass that we thought of, right? And one more thing, it gives you the validation of torque. See, observe what is happening. Observe it clearly. So it is actually rotating and coming. It is not coming like this. It is rotating. So it is experiencing torque. And this is a non-uniform magnetic field as well. Are you able to understand this? Right? This is what we mean by magnetic field is induced. So what will happen is if I keep these two in contact for some time, right? And after some time I remove them, you can see that this bell pin will hold the other bell pin even without the help of a magnet. Okay, that is a very important property of this substance, which is called as a ferromagnetic substance. I told you, we'll be learning about three: para, dia, and ferro. This is a ferromagnetic substance made of steel. So ferromagnetic substances have an important property associated with it called as retentivity. In the sense, they can retain magnetism. Are you able to understand what I'm trying to say? So they can retain magnetism. Based on this only, we divided the magnets into two types. One is a soft iron core and a hard iron core. If you remember in the previous chapter, when we discussed about galvanometer, what is the core of the galvanometer made up of? The soft iron core. And this is the reason. Because when you talk about an iron substance, it can have magnetism retained within it. What is the objective of a galvanometer? Not to retain magnetism. The objective of the galvanometer is only to show you current is there or not. So that is why you choose the magnet accordingly. Are you able to connect the dots? Right? So coming back to this point, it says a magnet induces magnetism. So it's like this. Magnet induces magnetism in this. In such a way, if you take the South Pole closer to this will become North Pole and this will become South Pole, even without physical contact. Magnet, magnetic substance, right? This phenomenon is called as magnetic induction. Why are you using the word induction? Because no physical contact is there. You're not rubbing one against other. You're actually taking one closer to another, right? When the north pole of a powerful magnet is placed close to the soft iron bar, the closer end of the bar will become south pole. That's what we saw, no? Right? Or else the attraction will not take place according to the third property, right? And the farther end is going to become the north pole, right? As a result, the magnet is going to attract the iron bar, and this induction precedes attraction. In the sense, the first property we saw, no, the attractive property. So this concept is also supporting the attractive property. It is supporting two things. What is it? One is the attractive property, and the second is like poles repel and the unlike poles attract. So all the properties are actually directing towards only one thing. Am I clear with this? So these are the five basic properties of magnets. Can we summarize it coming from the beginning? First is the attractive property. Second is the directive property. So directive property helps us for the navigation purpose. And what about the third property? Like poles repel and the unlike poles attract. What about the fourth property? When magnets always exist in pairs, right? You cannot define any monopole. You can only define a magnetic dipole. And the fifth property is about the magnetic induction. So without a physical contact, there will be a magnetism induced due to a magnet in which substance? Magnetic substance. Am I clear with that? So these are the 5 points. Just make a quick note of it. Mandarsra, you guys ask. No? நானும் சும்மா தான் சாப்பிட்டு போங்க புரியுதா கூடாது சமோசா சமோசா வேணும்னா கிளைமேட் நல்லா இருக்கு சார் சமோசா வேணும் second property is the directive. You want me to show the content? I hope you can write it on your own, or you want to see this. Where are others actually? மற்றவங்கள எங்க காணும்? ஆன்லைன்லயும் இல்லை. நிறைய பேர் இருப்பானுங்க. கல்பகேஸ்வர இல்லையா? ஆன்லைன்லயே இல்லை. 6 to 7 அட்டன் பண்றேன். அவங்ககிட்ட லிங்கே இல்லையா? அப்புறம் எப்படி அட்டன்? நான் வீட்டுக்கு போயிட்டாங்களா? ஒரே மழை நடக்கும். டிசைடே பண்ணிட்டு அந்த லீவ் தான் நாளைக்கு. என்ஜாய் ஃபார் we are in advance தானே? கரெக்டா? we are in advance only, no, in terms of syllabus. பரவாயில்ல, பிரச்சனை இல்லை. Don't worry, I'll complete it. So tomorrow no class. Okay. ஸ்கூலா? மைண்ட்ல இருக்கிற இன்வெஸ்ட்மெண்ட் சரியா சொல்லு. Right? Okay. So we find that. Priya. Bye. Bye.
Bye, sir. Thank you.
Yeah, tomorrow no class, okay? I'll announce.
Okay, sir. Thank you, sir.